All right, so we're going to do the exponential and the logarithmic models. So we'll do exponential first. That's the one that you did last year. Logarithmic will be the new one. So exponential, the rate of change, okay, and that's, you know, your derivative of a quantity, which we're going to let that quantity be y, okay, so that would be dy dt. So the rate of change of whatever you've got, and they won't use y if it's a word problem. Like oftentimes they're going to talk about a population and they'll use p. Do you know what I'm saying? Like they'll, because populations oftentimes grow exponentially. So it's not always y, it'll be whatever letter they choose. Is proportional to. So we use the letter K for that. It's K times something. That's what a proportion is. You know how you have the actual Statue of Liberty and then you have those little keychains that are in proportion to it. So it's scaled by some number. We just use K for that. Proportional to the amount that you've got. So the size of the quantity. So K times Y. So we are going to solve that differential equation. You want to move the Y to the left and the T to the right. So how would you move over the Y? Divide. So it'll be 1 over y dy, and then multiply over the dt, so k dt, and then we're going to do the antiderivative. And this is going to look like we've jammed every letter of the alphabet into this problem. What would be your antiderivative on this side? ln y. Now, it's tricky because there's a k in there, but k is just a constant. It could be 2 or 5 or 17 or whatever have you. The variable that you're doing the antiderivative for is t. So what would be the antiderivative of just k? kt plus c. I know, I told you, it's like we're jamming every letter of the alphabet into this. And there's actually going to be one more letter of the alphabet because how do you cancel out ln? E. So we're going to put e in there as well. So it's going to be y equals, e is a number, c is a number. So remember we put that c out front just as one big constant. So it's c e to the power kt. But if you want to write pert instead, because that actually sort of spells a word, I'm good with that. It is that formula. This is where it comes from. In pre-calc, we just hand you the pert formula and say, here it is, have fun. We can't explain where it comes from because you need to be able to do an antiderivative in order to explain it. But that's why it is what it is, right? C is your initial amount. And K is your rate. T is time. I don't usually go over that because people just know that T is time. And Y is whatever you're talking about. So again, like population or whatever it is. You can just use Y, or you can make the letter make sense for the problem. All right, here we go. You have to be friends with your calculator here. The rate of growth of bacteria is proportional to the number present. That is a sentence that just tells you it's exponential. Do you see that? Is proportional to the amount present. That means exponential. So you have to know, hey, that means exponential. We're using this PERT formula, right? There are 300 initially. So it's going to be y equals 300 e to the kt. 300 initially. And then it says there are 700 10 minutes later. So we're going to plug in 700 for the amount. So 700 goes in for y. And then 10 goes in for t, for time. And we're going to solve for what we're missing, which is what? What do we not have? Okay, you don't have the rate. Okay, so how would we start solving that? All right, 700 divided by 300 would be 7/3, and then that would equal e to the 10k. Then what? And it's which kind of log to get rid of e? ln. So we're going to ln both sides. That cancels that out. So we'll have ln of 7/3 equals, what was left? 10k. And then what's your last step? Okay, here's where the calculator comes in. You're going to type in ln 7/3 divide by 10 and get some crazy decimal, okay? Your ln button is kind of next to the 4. And just make sure you close the parenthesis after the 7/3 because you only want it to ln the 7/3, not the divide by 10. Yeah, it's on the left side. It's right below the log button, kind of next to the 4, sort of like diagonal from it. All right, what did we end up with? 0.084. Okay, you have to capture it because if you're going to reuse this number in the next part, you have to store it. Let's review how to do that. Store is right here, kind of next to the 1. So hit store. And you can store it as any letter you want, but I always do A because it's the first letter of the alphabet. So store alpha A, enter. Store alpha A, enter. Store alpha A, enter. I just always say it over and over again. Get everybody to remember it. Store alpha A, enter. Now, when we write this number on our paper, how many decimal points? 3. And I would truncate, so 0.084. So our equation, because this said write an equation, it would be y equals, what was our initial amount? 300? 300 e to the power 0.084t. That's your equation. Your equation should have a y and a t in it. Now, the reason we need to store that is for the part B. What is the number of bacteria after 20 minutes? Well, you would take 20 and do what with it? Plug it in for T. Just make sure you don't type 0.084. Make sure you do alpha A so it'll copy paste it for you. So here's what this should look like when you type it in. 300E. And how do you make the E show up? Second ln. And then alpha A for your stored decimal times 20. And that will give you your amount of bacterium. Now, if you had 700 after 10 minutes, after 20 minutes, you should have more. So you should be expecting a number bigger than 700. Did you get 1633 and a third bacteria? Okay. I guess you can have a third of a bacteria. I don't feel bad chopping them in half. Also, do you notice how this rate is positive? I get that it's a tiny decimal, but you get that it's positive. It means growing. Okay, if it's negative, it would be exponential decay. You would end up with less than what you had. So these are two words that kind of more come from chemistry. Do you remember these from chemistry? Okay, so doubling time is the time for the initial amount to be twice as much. So time it takes for the initial amount to be twice as much. The thing that messes people up about the doubling time and half-life is it's what gets plugged in for T. It's time. So it's what gets plugged in for T. Half-life is the time for the initial amount to be half as much. So it makes sense. Just remember to plug it in for T. Doubling time and half-life. Doubling time is usually fine because the word time is in there, but half-life does throw people off. Make sure you plug it in for time. These are both times. So let's try a couple of these. An element has a half-life of 1,500 years. Elements take a long time to break down. Initial amount of 200 grams. Find the amount after 10,000 years. So it would be y equals 200 e to the kt. 200 is what you started with. So just always kind of like begin there. Now it says half-life. That means you end up with half as much as you started with. So even though it doesn't say it in the problem, if you start with 200, what do you end up with for a half-life? Yeah, 100. So 100 is going to get plugged in for y. And it doesn't say that anywhere, but it's half of what you started with. Equals 200 e to the power k times 1,500. Good, our half-life. And then we're just going to solve that. So what would you do to start solving that? This is just like, what do you do to both sides? 100 divided by 200. Oh my gosh, it came out to a half for a half-life. Crazy. Mm-hmm. So a lot of people will even just skip this step and just write a half equals e to the 1,500k. Oh, and for doubling time, instead of a half, it'll be 2. All right, then what? ln. So you'll have ln of a half equals 1500k. Divide by 1500, and here's where you got to pick up your calculator. Yeah, so for these, we're doing like real world problems where it's an actual amount of something and you can't have a negative amount. So we kind of just don't use that for these problems. It just sort of doesn't come into play, the absolute value part of that.
Wait, let me dumb question.
No, I'm sure.
Why, like, it's half like 15 years, 15 years dimensional. Wouldn't you make the half-life 750 or is it just...
No, the half-life is what you're told. That's just kind of like a given piece of information. The half-life is 1500 years. What that means is it takes 1500 years for what you started with to be half as much. So whatever you started with, it's going to take 1500 years to be half as much. So if we started with 1,000 grams, after 1500 years, we'd have 500. All right, what'd you guys get for that? Did you get something crazy? Yeah, do you know what that means? Well, it is negative, so it does mean that we're ending up with less and less. This is how the calculator writes scientific notation. I don't remember what grade you learned scientific notation in, probably some point in middle school, but you remember like that times 10 to the negative whatever. So what this means is negative 4.6 times 10 to the negative fourth. What happened was the decimal point got moved over so many times that instead of writing 0.000 whatever, it just went to scientific notation. It kind of doesn't matter because we're just going to store it as A anyway. So do store alpha A, enter. And it says we want the amount after 10,000 years. So what you're going to type is, what did we start with? What was our initial amount? So 200 e to the power what? K times 10,000. Now we have that stored as A. So do alpha A times 10,000. It's a copy paste. It's taking that number and pasting it in there for you. Now, after 10,000 years, we should not have a whole lot of this element left. So did you get like a really small number? 1.968 grams. Or 1.967 if you want to round up. I just always say to truncate, though, because then you don't have to worry about it. After 10,000 years, and it's still hanging around. It's crazy. I don't know what the element would be, though. I don't do chemistry, only math. Just do the math part of the chemistry. All right, you're putting $500 into an account. It takes 6 years to double. As an aside, this will never happen because they're never going to give you a decent interest rate. They're going to give you like practically zero. Do you get what I'm saying? Like, I think the interest rate of my savings account is like less than 1%. Like, it's like going to be a decimal point of a percent. But anyway, just go with it. Okay. So you put $500 into an account. That's your initial amount. So y equals 500 e to the kt. Takes 6 years to double. I know it's not written in the problem, but if you started with $500 and it doubled, what do you now have? 1,000. So it's 1,000 equals 500 e to the power k times 6. And then you solve that. So again, you would divide over the 500 and oh my gosh, 1,000 divided by 500 is 2. And again, sometimes people will skip that step. Like if it's a half-life, they'll just put a half. If it's a doubling time, they'll put 2. Equals e to the 6k ln. So ln of 2 equals 6k and then divide by 6. And throw that in the calculator and you'll get your rate, which should be positive because the amount is growing. Question? No, that's a good question. It will technically not be correct. So you have to do ln of 2, close parenthesis, then divide by 6. It's like the order in which the steps are happening. Did you get 0.115? That's an 11% interest rate. That will never happen. Unless you owe money.
Yeah, it happens in the other way.
Yeah, the other way. Now, I don't think you would get an 11% interest rate, but don't be surprised if you get a 6, 7, or 8% interest rate on your like college loans, because that's life. Okay, what do we want to do with this to capture it? Store alpha A, enter. You can do K if you want. It's just I never know where K is. Like I only do A, B, and C because they're right next to the alpha button, so it's more convenient. All right, so what is this asking? How much do we have after 8 years? So what are we going to type? 500. Good. E. Our A times 8. Now it took 6 years to double. So in 6 years, we had $1,000. So in 8 years, you should have more than $1,000. So you should get an answer more than 1,000. Always kind of think about that because you want to make sure your answer makes sense. I got $1,259.921. I know it's money, but I would still just always do 3 decimal points because that's what they want on the AP exam, and just to be safe. You can put as many decimal points as you want. You just need at least 3 usually. Cool. Do you remember this from last year at all, sort of? This is the last, when I teach it, this is the last thing I do. It's like the very last lesson. It's not a very long lesson. I mean, how long did we spend on it? Like, not very long. Okay. All right, so the other model that we're going to do, that one was exponential. This one is logistic. I'm sorry, not logarithmic, logistic. And that's a common mistake. I can't believe I said that. So logistic model. So this has a carrying capacity, which is the upper limit L past which growth can't happen. So let me draw a picture to show you what this is going to look like. Or have you heard of this before?
Yes.
Oh, cool. Well, hopefully I can like build on or clarify anything that you didn't understand before. Oh, well, no, I think it should be the same. Here, you know what? Let me draw my graph a little bit better there. So let's start with a picture because I think a picture helps oftentimes. What you're going to have is this carrying capacity, this horizontal asymptote at this value L. And it's going to look like this. You're going to level off at 0 on this side and then come up and then level off at the carrying capacity on this side. And this is often used for populations as well. Like you can use an exponential growth for a population, but like this is actually more accurate because realistically, there's going to be a limit where your population can't grow anymore. And I think I have like a population of deer here. Let's talk about that. So like, say the deer don't have any natural enemies anymore and they just keep growing and growing and growing and growing and they get above this carrying capacity. There's not going to be enough food for them to eat. Do you get what I'm saying? And there's not going to be enough space. And so then their rate will start to decrease. They'll start to die off until they get back below this like carrying capacity. And if they go above that, they're going to start dying off. Do you get what I'm saying? Like there's that carrying capacity where it's going to level off. And if they go above it, then their rate is going to start to decrease again. You're smiling. Is this what you talked about in environmental science? Like exactly. Okay, perfect. Okay, so let's write that down. If Y stays in between 0 and that L value, so if your amount of your population or whatever it is you're talking about, if it stays in between there, then the rate of growth is positive. That dy dt is going to be positive. You're going to keep growing. You'll keep having more and more deer or more and more whatever it is. But if the amount goes over that carrying capacity, so if it somehow gets above that, then the rate is going to be negative until it gets back below that limit. Does that make sense? Good. Did you all take environmental science? Oh, okay. That's what I took too.
We're learning that Actually, just
So you can bring up that you're talking about it in calculus. Okay, growth is fastest. And they love to throw a question like this on here, and it's a really simple thing if you can remember it. Growth is fastest at the inflection point. And let me relate it to the picture. Do you see how for this portion we're concave up? And then like right here in the middle, there's an inflection point and then it changes to concave down. Do you see that? I mean, I know I'm not a great artist, but do you see concave up and then here it switches to concave down? That value is half of L. So it's at L divided by 2. So if you just take whatever that carrying capacity is, divide it in half, that's where the inflection point is. And that's where your growth is going to be the fastest. And that should make sense. Like if you were to draw in a tangent line here, do you see how it would be steepest at that point? Okay, so that's where the growth is going to be the fastest. Now, you know how we like worked this one out? We're not going to do that. I'm just going to give you this one and you're going to kind of have to remember it. Okay, I'm sorry. So it is y equals L over 1 plus CE to the negative KT. Now, before we all freak out, and I'm not done giving you formulas, I'm sorry. Do you see this portion right here, how it's CE to the KT? Do you see that? It's the same as the other one. You just make that negative, and it's L over 1 plus that. Did you do that in environmental science? Okay, that's the new thing then. You get the actual like mathy part of it. Okay, so this is CE to the KT, kect or whatever, pert. Okay, just make that negative and it's your carrying capacity over 1 plus that. There's 2 different ways the dy dt can be written. So it can be k times y, parenthesis, L minus y. Or it can be k times y, 1 minus y over L. And I actually don't really understand why there's 2 different versions, but I've seen both of them on AP questions. So that's why I'm showing you both of them. And when I asked, the best explanation I got back was, well, K can sort of be manipulated depending on like how you word the problem, because K is just some constant that you could fiddle with. Do you get what I'm saying there? Like it just, so anyway, they're practically the exact same thing, but I'm bringing up both of them because when I went to pull AP problems, I've seen it written both ways. And I'm like, well, I better show my class both of them. Okay. So here we go. Got our calculator? We're all ready? A deer population follows this growth rate. Real quick, what's the carrying capacity of deer? And don't overthink it. When you look at this, what's your carrying capacity for your deer? 4,000. Do you guys see that in there? Don't overthink it. It's going to be like the number that's in the problem. So if you go over 4,000 deer, they're going to start dying off until it gets back below 4,000. Okay, so 400 is our L. 40 deer were released initially, so that's at time 0. And then there's 104 deer 5 years later. So we're going to have to go through and find all of the things that we're missing. Let's start with that 4,000 though. It's going to be y equals 4,000 over 1 plus, and then it's CE to the KT, but just make it negative. So it's the same as what we just did on the other side of the paper, but just make the K negative. Now we're going to plug in the other information. So we have that carrying capacity. 40 deer were released initially. So Y is going to be 40 at time 0. Now let's do a little bit of this in our head, because then there'll be less that we have to write. If you plug in 0 for time, negative K times 0 would just still be 0. What is E to the 0? 1 times C would just be C. Do you see how the rest of that went away? I wasn't going to write it all out if we can just do it in our head. And 0 is a nice number to plug in. All right, welcome back to like algebra class. We had to figure out what C is. So what would you do to both sides to start algebraically figuring that out? And I'll give you a hint. We need to put parentheses there. Multiply by 1 plus C. We're going to multiply that to the other side. All right, then what? Divide by 40. Go ahead. Oh, it was given in the problem. It said 40 deer were released initially. So I plugged in 40 for the amount. And then I plugged in 0 for the time because it was initially. And that's why all this kind of went away, is because we plugged in 0.
Why is that not C?
C is not the initial amount for this one. You have to find it. Yeah, see, this one's nice. C is just what you start with. This one does not work that way. All right, so we're going to divide by 40. If you divide both sides by 40, what are you going to get? It would be 1 plus C equals, one of the zeros will cancel, 100. And so C is 99. So yeah, C unfortunately is not the initial amount in this. But we found it. It's 99. Okay, so let's start back over. Y equals 4,000. I'm basically starting like a new problem here. 4,000 over 1 plus, and now I know that C is 99. The other thing we're missing is K. So go back to the problem. We have one more piece of information. What's the other thing that we know? Good, so where am I going to plug in 104? For Y, that's your amount. And then I'm going to plug in 5 for time. So 104 equals 4,000 over 1 plus 99e to the negative 5k. Now what? Gonna be a good bit of steps here to try and like work through this. Hint, you need parentheses here. You would multiply all that over, okay, and then you would divide by 104. So if I multiply all this over, it'll be 1 plus 99e to the negative 5k. And if I divide over the 104, let me just type that in real quick. 4,000 divided by 104 gives me this, 38.461. All right, we're getting closer. Now what? Still trying to get K by itself. You would subtract 1. Let me just put -1 and I'll erase this. Then what? Divide by 99. Yeah, so let me go ahead and type that in. I've got this 38 point whatever. I'm going to -1. I'm going to divide it by 99. And then I do want to ln both sides. Now I have to ln this number. That means I'm going to have to store it. So let me store this as A. And then when we ln both sides, I can ln A, if that makes sense. I'm going to like copy paste it. So I stored it. Let me clear all this out because this is getting a little bit too jumbled there for me. So we'll have negative 5k equals ln of that A value. So negative 0.971. And then what's your last step? Divide by negative 5. So the negatives are going to cancel. K is 0.194. And I'm going to store that as A. Yeah, so you had to ln this entire thing. So what I did is I stored that. And then I ln'd the stored value, like I did a copy paste. And I just always keep using A. I just keep covering up A. Every time you store something as A, it covers up what you had before. If that bothers you, you can store something as B or C, or store it as K if you want. But I just store everything as A. All right, so if you're going to write out the whole equation, it is Y equals 4,000 over 1 plus, what did we get for C? It was 99, right? 99e to the negative 0.194t. So that's like your official equation for the whole thing. But you're just finding all the missing pieces. I get that the calculator work is intricate. I get that that's a lot of typing and a lot of storing. But in essence, you are just plugging in what they gave you and solving for what you're missing. So at the end of the day, that's what you're doing. How would we answer B? What is the deer population after 15 years? Well, you're going to take 15, plug it in as T, okay? So this is going to be 4,000 over 1 plus 99 e to the power negative alpha A times, oh, I forgot what it was already, 15. So after 15 years, it's how many deer do we have? I got 628 deer.
Oh, not get that.
Okay, let's round to the nearest whole deer. Let's say 629 deer. I don't mind like chopping a bacteria into pieces, but a deer, that's like, let's do like a whole deer. And then what is the limit as time goes out forever? Where will the deer level off? 4,000. Why? That's your carrying capacity. That's where it's going to level off. I'm not going to make you do that again. This one, you're given the logistic model. So there it is. Verify that the carrying capacity is 4. You can see that it's 4 because there's a 4 right there. But I found one on an AP question like this, so I put one in our notes. Verify that that's 4. So you would do limit as time goes out to infinity of this thing. And it's really kind of a silly question because we know it's going to be 4. I guess they just want you to write a limit. I don't know. But limit as time goes out forever, it should level off at 4. So here's what happens. You get 4 over 1 plus. Now let's look at what happens as time gets bigger and bigger. The exponent gets bigger and bigger and bigger, but it's a very large negative number, which flips that. So instead of like 100 billion, you get 1 over 100 billion, which is essentially nothing. And so that ends up being 4. I saw one like that on a release problem or like a practice problem. So I was like, here, I'll throw one in the notes. But you just do the limit as time goes out forever. Find the point of inflection. Ooh, if you remember what I told you up here, that's going to be really easy. Where's our point of inflection? Half of L. It's halfway there is where your point of inflection is going to be. So it's going to be L over 2, which, what did we just say L was? 4. So 4 over 2, which is 2. Now here's the thing. That's the Y value. Y is 2. If you want the time, you have to take 2, plug it in for Y, and then solve it. Okay, so we're going to solve one more. You're like, we hate you so much right now. So you're going to take 2, plug it in for Y in the equation, and then we're going to solve it. This one won't be as bad though, because we have some like nicer numbers here. They're at least whole numbers instead of decimal. So what would you do to start solving that? Multiply by that stuff and then divide by 2. These are going to switch places. So you're going to get 1 plus 2e to the negative 3t equals 2. Okay, good. You guys are coming with me there. Because if you divide the 2 over 4 divided by 2 is 2. Okay, then what? Minus 1. That's the same steps we did up here when I subtracted the 1. It's just, it was a weird decimal minus 1. Here, we were able to just do 2 minus 1 and get 1. So it turned out nicer. All right, then what? All right, divide by 2. So these are all the same steps, but nicer numbers. ln and then divide by negative 3. And that will give you what the time is. So type in your calculator, ln of a half, divide by negative 3. And don't stop listening to me as soon as we finish, because I want to draw a picture of this so you actually understand what we did. And it should be a decimal, 0.0. 231. So here's what this would look like. Your carrying capacity is at 4. It's doing something like this. And this inflection point is at 0.231 and then 2. Do you see that there? Like that's where that is. I feel like the visual helps with that.